16. Another dilution question. So we're going to dilute. That means we're going to use M1V1 equals M2V2. I can see right here, my numbers are grouped nicely. I've got a molarity and a volume linked to each other. And remember, when you see this magic word of connecting two numbers, it almost always means you're going to be multiplying those two numbers together. Okay, this one times this one in your math. Well, sure enough, M1V1 would put those numbers next to each other. 8.00, that's my M1. V1, 1.19 milliliters. So they're all being multiplied in my math. Equals M2, well, we've got that, 1.50 molar times V2. And the question's asking, what will the final volume be, or what will the volume be? They're diluting it too. And so divide by 1.5, divide by 1.5, and we should come up with an answer of, in milliliters, 6.35 milliliters. Now, if you're converting things to liters first, you'll get all your answers in liters. Just be paying attention to the units that come with those questions. All right. We've got a couple more dilutions here. I'll tell you what, just in the sake of not being so terribly redundant, these two questions are very much like the dilutions questions that we've already been doing, 17 and 18. 19 is also quite like the ones we've been doing. Actually, let's look at 19 because it's worded just a little bit differently. It tells me we've got a 3.8 molar solution that's being diluted. So right away, I know this is an M1V1, M2V2 question. 3.8 moles per liter. And the volume is what? Well, we don't know yet. Let's see here. In the end, it's diluted to 8 times its original volume. And they want to know what is the molarity of the diluted solution. So M2 is what we're after, the molarity, right? What is the molarity? That's our M2. So how are we going to do this if we don't have any other numbers? Well, it really is a case that it doesn't matter what volumes you choose. We're diluting it 8 times to 8 times its original volume. So just pick an easy number. I'm going to go with 1 liter. And it's diluted to 8 times its original volume, so now we've got 8 liters. This might be like how you get a recipe for like a concentrated drink mix or something, and you have to dilute it to 8 times its original. Or if you go to like make orange juice from the frozen can, and you take 1 can of that and put in 3 cans of water, you've diluted it down to 4 times its original volume. So the same kind of idea here. You could pick any numbers you want in those places as long as the connection from here to here is 8 times. Right, so as we move across, it's 8 times larger. And again, any numbers would work. So, with that in mind, let's go ahead and solve for M2. Punch it into my calculator. I've got 3.8 times 1 over 8. That'll cancel us out. And 3.8 basically divided by 8 is what we're up against. M2 equals 0.475 moles per liter. And that's the answer that you'll get if you do this right, using any volumes at all. Okay, for the starting volume and then 8 times its original volume at the end. You could use 2 and 16 or 1 and 100 and 800 milliliters or whatever. It would work the same way. Okay, let's look at 20. This one's kind of a classic story. We see questions like this often just because it kind of makes an interesting story, and it's something that could happen. So a solution, a chemist has 480 milliliters of a solution with 2.50 moles per liter solution in water. And then a week later, the student, or rather the chemist, wants to use the solution, but the stopper was left off. So somebody left the doggone cover off, and a bunch of the water evaporated out. Now think about that. If you've got a solution that water has been evaporating from for the course of a week, you're going to have you're going to have a somewhat more concentrated solution at the end than you did at the beginning, right? It's getting more and more concentrated as the water evaporates. It's kind of the principle behind how the Dead Sea gets so salty, right? Because salty water runs in there and the water evaporates, and then the salt's concentrated with time. So in the same thing here, we're going to go M1V1 equals M2V2. So our original molarity was 2.50 molar. The original solution volume was 480 milliliters. And at the end, it got more concentrated. We need to figure out what that M2 is. What is the new molarity? So that's that guy right there. But what's the new V2? Now you might look at it and say, oh, it's 39 milliliters. It's not 39, right? That's how much left. That's how much of the water evaporated off. So if we had it in a flask, 480 milliliters, and you lost 39 milliliters, that's how much has been lost from the original solution. So the volume that goes in here is going to be the 480 we started with minus the 39 that were lost, which comes out to 441 milliliters. Right, so it's getting slightly more concentrated with time as this reaction takes place. So from there, solve it out, divide to get the M2 by itself, and you should come up with an M2 of 2.72 moles per liter. Now, it's not a whole lot more, but it definitely is an increase. I mean, it's a notable increase from here to here. If I was using that solution for a reaction, I'd want to know that the concentration had increased, nearly 10% more concentrated than it was before. All right, let's see what's next here. 21 is based a little bit, it seems to be based around dilution, but it also has a mass in there at the end. Okay? So we need to do a little bit different work with 21 because it doesn't just end on a molarity or a volume. And this one's got a little bit more to it too because the student here in the story is taking portions of the solution out. So 21 is probably one of the more complicated questions on this whole sheet or on this whole collection of questions because it's kind of a lot going on that you have to keep track of. The student here starts out with a 0.6 liter solution. Okay, so if we imagine that in a bottle, 0.6 liters of solution in a bottle, and that would be then 600 milliliters. From that, the student takes out a 20 milliliter portion, okay, a 20 milliliter sample of the stock solution. So we've got the same stock solution here. The student's taking out just a small amount of it. We do this quite a bit in chemistry techniques because we don't want to use the whole sample. Maybe we don't need that much, or we need to save most of it for later, or we need to make sure that we have enough to do the same experiment consistently the same. So he's using or she's using only 20 milliliters out of 600. That's basically like choosing 1/30th of the sample, 20 out of 600, 1/30th of the original whole solution is what the student's using. And that's just kind of, I think, a random choice here. They could have used 10 milliliters or 40 or something else, but they've gone with 20. And then what? Let's see. They then take and add 130 milliliters of water to that. They dilute it with adding then 130 milliliters of water. So what will the whole solution's volume be? Well, they're going to add 130 milliliters of distilled water to dilute this down. We'll have a total now of 150 milliliters at this point, right? So we're just kind of following what the student has done. And at this point, we know that the solution is 150 milliliters, and we know something else about it. We know that it's a concentration at this point of 0.25 moles per liter. So I'm going to write that down here too, 0.250 moles per liter in this solution. That's our solution that we know everything about. They're not so much asking us to go back and figure out the molarity of the original solution directly, although that kind of seems like it's part of what's happening behind the scenes. They want to know how much copper chloride was used to make the original stock solution. In that first solution of 600 milliliters or 6.6 liters, how much copper chloride would have been dissolved into there so that what's described in our notes here so far actually works out, and that we get that concentration that we think is going to be there? Well, there's a couple ways to go about it, but what I'm going to do is figure out how many moles are in our solution here at the end. How many moles of copper chloride, that's CuCl2, right, are in this solution that we presently have at the end of our notes here so far. So to find moles, I'm going to take 0.15 liters times the molarity of 0.250 moles per 1 liter. I'm going to multiply that out, and that's 0.0375 moles of copper chloride. Now, that's not grams, so that's not quite the answer here. Plus, that's not the whole solution. That's only that 20 milliliter portion had that in there. So the original sample, to go back this way now, is actually 30 times more copper chloride to get back to the original solution, because that's a much larger container, and we've only pulled out a little sliver of it, a little sample of it. So what's 30 times this amount? We're going to go times 30 in the original solution, the big batch of it. It's kind of like saying I've got one cookie, and in my batch there are 30 cookies, and if I look at my chocolate chip cookie, there are 7 chocolate chips in it. So how many chocolate chips were in the whole batch? And we just take a look at our cookie and say, oh, there's 7 chocolate chips, and I have 30 cookies. So if I assume that this is an average, that there's 7 in each cookie, then there's 210 chocolate chips in the whole batch. It's kind of what we're doing here, except we're doing it with solute, which isn't nearly as fun as a chocolate chip cookie sort of story. But what does that come out to be? 0.0375 times 30 gets us back to the number of moles that were in the original solution, or yes, in the original solution before we broke it up. And that's 1.125 moles of copper chloride in the original sample. Okay. And we got one more little step to go because they want that into grams. So I'm going to take that 1.125 moles and convert to grams of the same. 1 mole is how many grams for copper chloride? We can go add it up off the periodic table. I get 134.46 grams. All right, multiply that out, and we're sitting at 151.3 grams of copper chloride. So that's how much of the solid was put into water to make the original solution, if we take that back there, in this solution. And if you think about it mathematically, we just kind of pulled things out of there. We worked our way down through the page here. At the end, it should be able to circle back around again, because if we haven't spilled anything or nothing's evaporated and changed, that should still be the amount of solid that would be present in there at the end, by math and by reality in the actual bottle in our stockroom. Okay, let's look at 22. Ocean water contains a lot of salt. Well, we know that it's salt water in the ocean. There are lots and lots of other salts in the ocean, but sodium chloride is one of the most predominant ones that's there. And so there's lots of it. How much? It says here we've got 0.598 moles per liter. And, okay, that's 0.598 moles per liter, or molarity. They want to know is how much ocean water would it take if you needed 1,000 grams of salt? So if we're going to take ocean water and dry it to get the salt out of it, and then use that sodium chloride like sea salt, it's kind of what they do to get sea salt. They take saltwater brine like that and they let it evaporate in these big kind of evaporation ponds, and then you get this nice crystal salt at the end, and then they kind of break it into little chunks and put it in a bottle and sell it to you. So if they need 1,000 grams, if I want 1,000 grams, or 1 whole kilogram worth of sodium chloride, how much ocean water will I need? What volume? That's down here. That's volume, or liters of ocean water, which is our solution here. But now we can't just stick 1,000 grams in here, right? Because 1,000 grams doesn't go up there. This needs to be in moles. And so the first thing we need to do is convert that into moles. 1 mole of NaCl is 58.5 grams of NaCl. Take a moment to quickly divide that out. 1,000 divided by 58.5 gives us 17.1 moles. That's how much salt I need, 17.1 moles of salt. And if I have X liters of seawater, I'll have 1,000 grams approximately of salt. So what does that come out to be? Well, do your math again, as always, rearrange and solve for X, and X should come out to be 28.6 liters of water. Think about that. You only need 28.6 liters of ocean water. That's not that much, right? That's like maybe 7 or 8 gallons of water, and there's 1,000 grams of salt in there. It's insane. You think about how much salt, like that's enough salt to fill the average, like recommended amount of salt, a maximum amount of salt. I think they recommend to you this day something around 2 grams of salt intake per day for people. Like that's what's on the guidelines from the government. 2 grams. This would be enough salt to take care of your salt needs at the maximum recommended level for about 15 months. So think about that. In a little bit of seawater, there's enough salt for the average human to be perfectly salty for well over a year. That's some salty water. And I don't remember. I've been to the ocean a couple of times. I can't remember the taste being especially salty. I don't remember the taste of it at all necessarily, but I know if you get to the ocean and you can swim in it or something, you're bound to get a little bit of a taste of it. And yeah, it's definitely pretty salty. All right, let's look at 23. What's the molarity? All right, so I need molarity. Molarity equals moles over liters. We just used that one. So we've got how many liters here? 0.275. Move that decimal over 3 times. And we've got how many moles? Well, we don't have moles yet, but we can get them because 90 grams is the solute in H4Cl. We can convert that into moles relatively easily. Do this quite a bit. We need to know that 1 mole of NH4Cl is 53.49 grams of NH4Cl. And then 90 grams would give us 1.68 moles. Bring that around, stick it into that molarity equation up at the top, 1.68 moles in a 0.275 is some molarity of about 6.11. There we go. All right. 24. A chemical test has determined the concentration of a solution to be 2.41 molar. All right, 2.4, oops, I wrote liters, 2.41 moles per liter. A 100 milliliter volume of the solution is evaporated to dryness. So we took that solution and let the water evaporate or heated it gently overnight and dried it all the way out until we had crystals left. I think everyone's done this by now this year, at least once. And they took 100 milliliters, so that's a 0.1 liter sample. And at the end, there were 9.56 grams of crystals in the evaporating dish. 9.56 grams. Calculate the molar mass. The molar mass, remember, and I tell my AP students this a lot, when you're facing a question like this, it's really important that when you say calculate the molar mass, that you know in the end what will the units be on molar mass. Because if you know the units of your answer that's needed at the end, it's a lot easier if you're not positive how to get there to figure out a successful route. Well, molar mass is always in grams per mole, right? So when we're looking for molar mass, we need this to be in grams per mole, which means I need grams and I need moles. I'm going to divide them into each other. That's it. If I have grams and moles for my solute, I can divide grams by moles and I'll have my molar mass. Well, I already have grams. Here's 9.56 grams of crystals. I just need moles now. And what do you know? But right here in this spot of our equation is x, and that's in the moles position, right? So if I take a moment now and solve for x, figure out how many moles this will be, x will be 0.241 moles of unknown solute x. Okay. And now I've got grams and I've got moles, and I can put those two things together to get molar mass. So 9.56 grams of solute that were collected, and based on the concentration and the volume that they gave us, based on the concentration and volume that we know the solution contains, that I collected from that, or I must have collected from that, 0.241 moles. That's what it would take for that volume and concentration to be correct. 9.56 grams divided by 0.241 moles gives me a solute with a mass of around 39.67 grams per mole. It's a little different units than we're used to, but notice again that they're in the math, grams on the top, moles on the bottom, so the units in the end then must be grams per mole. Now, you might in some cases be asked to figure out then, okay, so what is it? What's the solute? The unknown substance. What is it? Well, it's something with a mass of about 40 grams per mole. And something that comes to mind right away, you wouldn't have this probably popping into your head unless you've just spent a lot of time around chemicals, that it could very well be sodium hydroxide. Sodium hydroxide has a mass of about 40, exactly 40 grams per mole, almost exactly on the button. So maybe, we don't know. This question doesn't ask us to figure out like what the solute is, but if you had to suggest something, you'd look for a compound that had a mass of about 40 grams per mole. In this case, sodium hydroxide is possible in terms of its mass. We don't have enough information here to talk about how they did the dehydration and all that kind of stuff, but sodium hydroxide's it's kind of tricky to get crystals from sodium hydroxide just because it's the nature of that chemical. Such a strong attractor of water, it's tough to do that. But that's just sort of beyond the question. All right, 25, tincture of iodine. A tincture of iodine is a solution that they use for they used to use it more, but I think they still use it in some places for disinfecting your skin, like before sticking a needle in, like if you're giving blood at the blood bank, they used to use iodine to sort of scrub off the inside of your arm. They still use iodine-based solutions, I think, in like surgical prep. So if you ever have a surgery and they have to cut into your skin, and then you look at it afterwards, sometimes there's like a kind of a orangish brown sort of stuff that's left behind around the place that they did the incision, because iodine's a really good disinfectant. And a tincture of iodine is just a solution where they usually dissolve it into alcohol first, because iodine's not something that dissolves very well into water, so they have to dissolve it into alcohol first, which will dissolve it because it's kind of nonpolar, and iodine's very nonpolar. And then they can add water to it, and it dilutes it out, spreads it out. So that's kind of what this story is about. They're preparing tincture of iodine with 34 grams of iodine. They dissolve that first into 25 milliliters of alcohol, because that's what dissolves iodine very well. And then they dilute it down to a final volume of 500 milliliters with distilled water. Okay, dilute it down to that. And they want to know what's the molarity in the final solution. Well, in the end then, molarity, we're not going to use the 25 milliliters because the final solution isn't 25 milliliters. The final solution is 500 milliliters. And we aren't even in this particular part of this question interested in the KI because it doesn't ask me anything about the KI. So I'm not going to use, I'm not going to use that either. And so you might look at this and say, man, there's just too dang many numbers for me to do anything. Well, I don't need that because we're not interested in the KI. We're just interested in the iodine. And this 25 milliliter of ethanol along the way is just kind of part of the instructions or part of the recipe for how to make this solution. But in the end, we're not too interested in using that either because by the time we get to the end, even that ethanol has been very, very diluted down in this solution. What we really care about is the molarity of the iodine. And remember, molarity is moles of iodine divided by liters of solution. Well, we already know the final solution is 0.5 liters. What's the moles on the top? All right, so we're going to go ahead and do that conversion. I kind of got a little tight here, so allow me to sort of slide things away. Okay. 34 grams of iodine is how many moles? That's what we'll need to do here. So 1 mole of iodine, go to my periodic table, add up iodine, so twice the mass of iodine, and we come in around 253.8 grams of iodine in a mole. It's a diatomic element. How many moles is that? Plug in my calculator. 0.134 moles of iodine are being dissolved in this solution. So I'm going to put that in up here, 0.134 moles over 0.5 liters, and we get a final concentration of 0.268 molar iodine. Now, in some company somewhere, they're making tincture of iodine up and then sending it out to the places like surgical units and hospitals and so on that need it. They don't make it at the hospital, I don't think, ever. They get those sort of things shipped into them. But there's a recipe that's based on the concentrations that they know they need. And I'm sure there's been a lot of experiments done over the years to figure out what's the concentration of iodine that's necessary to kill off all the germs before we do surgery. And then they make that concentration. And maybe this is the recipe. I don't even know what the concentration is for the stuff that you'd actually get spread on your skin before surgery. But if I'm in charge of that company and I'm making it for the folks at the hospital, I'm going to make it as strong as they need it to kill off the germs effectively. But then not any stronger than that, because the more chemical you have to use, the more expensive it's going to be, the more potentially risks there would be to the patient to have it on them for too long, or too much iodine maybe would just cause other sort of side effects. But certainly just less chemical is better. So you want to use as much as you need to get the job done, but no more than that for various reasons. And maybe that's the concentration of iodine that they use. I don't know for sure about that. If you find a resource that tells you the actual recipe for iodine they use in surgery, I'd be really curious. All right. What mass of H2SO4 is in 60 milliliters of a 5.85 moles per liter solution? Again, we can start to fill in our equation pretty quickly. This is a 0.060 liters of solution. That's this, turned into liters. 5.85 molar. How many moles is that going to be? So multiply it out here. X, we crisscross or cross multiply here. Our X should come out to be, I have that number. 5.85 times 0.06. X equals 0.351 moles of H2SO4. And we need that in grams, so I'm going to go one step further and say that 1 mole is 98.08 grams of H2SO4. And that should come out to be 34.43 grams of H2SO4. Now, just to kind of show you too, we can almost sort of set this whole thing up as one, what looks like a mole conversion, or what a lot of you call stoichiometry problem. And Mr. Mitchell's more of a fan of I think setting it up this way when he does these too. So actually no, I think Mr. Mitchell would like it this way more. I would do more often the other way. But let's quickly show you the other way, so you can kind of see maybe this is the way you would set it up. 60 milliliters of solution. It's a 5.85 moles for every 1,000 milliliters of solution. And then 1 mole is 98.08 grams. So we're using exactly the same math as we did up above, just arranged a little bit differently, and we still get the same 34.43 grams. So either way, you're going to get the same answer, whether you organize it using the molarity equation, which is kind of what this is, and then converting your answer from moles to grams, or if you just do it as sort of a mole conversion series where the units kind of cancel out like we do in the bottom. So whichever way is your preference is perfectly fine. All right, 27. How many moles of H2SO4? This is the easiest kind. We've got a 4.25 mole solution. Let's try that again. 4.25 moles per liter equals X moles over 2.50 liters. It's so important that you know these equations and know what units go where, right? Because then as soon as you see numbers in a question, they just sort of find their home and they drop right into the correct places in the problem, and then we know exactly what we're left with in the end, right? So cross multiply, solve for X here, and you should get an answer of 10.6 moles. We don't often solve for moles because we can't go in the lab and measure out moles, but that's what this question asked, so that's what we'll go with. 28. What mass of cobalt chloride is needed? This is kind of like the last question, except instead of moles, they need mass, so we're going to take it one step further, kind of like we did up on 26, all right? I've got a 4.00 molar solution. What mass, though? Let's see, where in this equation is mass? I've got 650 milliliters, that's 0.65 liters. Where the heck is mass? And then I got X up here. This is in moles, right, on the top. And I can get this answer X and then convert to grams from there, right? So this is one way to sort of set that up. Cross multiply and get moles. And then make the conversion from there. So 4 times 0.650 gives us 2.6 moles of cobalt chloride. I rounded off a little tight on my decimal, so I'm going to go back to 2.60 moles of cobalt-2 chloride. This might be a case where that formula is not as familiar to you, where cobalt-2 means cobalt with a +2 charge. Chloride has a -1 charge, so 2 plus 1 minus, I'm going to be COCl2. So I need that to be in grams, though. So let's take it one step further and say that 1 mole of cobalt chloride with that formula has a mass. Go to the periodic table and add it up. 129.8 grams. And that should give me a mass in the end of 338 grams of cobalt chloride solution. Cobalt chloride solid, rather, dissolved to make this solution. Okay. Just a few more questions to go in our long set here. And then we'll be done. A student wants to make a solution, 0.150 molar solution, 0.150 is my concentration, of silver nitrate, AgNO3, and has a bottle with 11.27 grams of silver nitrate. That's one of the most expensive chemicals that we buy in our chemical stockroom because silver prices are so high that even silver nitrate is expensive because think about it. Where do you think they get silver nitrate? You don't just find that laying around on the ground. They have to make silver nitrate, and they have to make it from silver. And that's what else are you going to use? And so if silver is expensive, then anything made from silver is expensive. Even chemicals for us in the stockroom, very expensive. What will the final volume of the solution be? So that's going to be down here. If we use up all that salt, all that silver nitrate. Well, silver nitrate, 11.27 grams. That's not in moles, but we're going to need to get it into moles if we're going to plug it in here and solve, right? Because to plug in up on the top of my numerator here on the top, we're going to need this in moles, as we often do. So convert 1 mole of silver nitrate is, added up, 169.87 grams. That gives me just a small amount, 0.06634 moles. And so that goes up on the top of my numerator here, 0.063, oops, got a little ahead of myself, 6634 moles. Do your math, solve for X, and X should be 0.442 liters, or around 442 milliliters. Okay, 30. We're back to energy drinks of the old-fashioned variety, just flat out pop. Now, no caffeine in Sierra Mist, but there is carbon dioxide in there. and it has a concentration of 0.0523 moles per liter in this story. 0.0523 moles per liter. That's our big M. How many grams of carbon dioxide would be found in a bottle of Sierra Mist with a volume of 591 milliliters? That's my volume of my solution. How many grams of CO2? Well, I can solve for X in moles and convert it, right? Easy enough. So in 30, I would need to multiply those two numbers together to get my moles. 0.0523 times 0.591. We get an answer here of X is 0.0309 moles of CO2. And 1 mole of CO2, according to my periodic table, is 44.01 grams of CO2, for a total in that can of 1.36 grams of CO2. Now, you might not think that sounds like much, and it's really not, but it's a gas when it comes out of the soda, right? So this might be like, oh man, what if I slam a whole can of Sierra Mist, and then afterwards I got to burp like crazy? Why? Well, a big part of why is because all that fizz that's dissolved into the soda, all that carbon dioxide that's dissolved, when it gets into your stomach, that gas comes out of the solution. Part of it is simply because it's been stirred up as you swallow. Part of it's because your body's warm and gases don't stay dissolved in warm water very well. And so they come out as a gas. And so that gas has to go somewhere if you don't want to have it in your digestive system and have it, the pressure hurts in there. So we burp it out. Well, 1.36 grams of CO2 doesn't sound like much. In terms of like 1.36 grams, that's like just a little bit. But a gas spreads out into such a large volume that 1.36 grams takes up a lot of space. If you were to imagine how much air space that takes up, it's actually quite a bit of volume. And if you try to imagine keeping that much of a gas volume in your stomach, you'd be uncomfortable really soon trying to hold that much gas in, which is why we burp, which is, that's what it is. All right, 31 asks, if we've got a solution in a flask of sodium acetate, how would we decide if the solution is saturated or unsaturated or supersaturated without knowing how much is in there? And that last part is just there to say you can't just look at the number or the mass and then go look at the solubility curve for this compound and see where you are next to the solubility curve. So we're not allowed to use that curve. We have to think about it. We have to experiment to do it. And we may have talked about this one in class already. I don't remember if I've mentioned it in every class. I think so. But the idea is that we need to understand the differences between these three and then how we'd identify those differences in a solution that's unknown. The easiest thing to do, if you can, in a flask would be to drop a crystal of sodium acetate in there. Drop a little sodium acetate crystal in there. So just one little speck. And heck, even a crystal of maybe something similar would work. It's just you wouldn't want to contaminate your solution with something else. So if you have a little sodium acetate, you just grab one tiny little crystal, drop it into this solution. Usually one will do, maybe 1 or 2 crystals. And when it hits the solution, one of 3 things will occur, depending on what sort of solution it is, right? If the solution's unsaturated, and I add a crystal to it, what's going to happen? Well, unsaturated means that not quite or something less than the maximum has been dissolved. So if you add more, there should be room for it, right? It should be able to dissolve. Crystal will dissolve. The new crystal. I didn't write that part down. I should have. Add a crystal of our stuff, of our solute here, sodium acetate. And here's the 3 possibilities, right? If it's unsaturated, the crystal will dissolve. So if you did that and it's gone into the solution, oh, there must be room for more, therefore this is an unsaturated solution. What if it's saturated? That means it's holding the maximum amount of stable dissolved solute. If it's holding the maximum and you try to add one more crystal, there won't be room for it. So this crystal won't dissolve, there's no room, it'll just sort of hang out. Usually that crystal is pretty dense, so it'll sink to the bottom and just lay there on the bottom. If we think about it, sand in the ocean lays at the bottom of a large solution. If you're at a beach up to your waist or something like that, you're surfing, you're swimming, you're hanging out, taking selfies in the water, and you look down, you're standing in sand because that sand isn't dissolving into the ocean, right? Does sand dissolve? Well, we don't think so, but just a teeny, teeny, tiny bit of those different minerals in sand does dissolve. And the reason that there's still sand under your feet is because it can't all dissolve. That's the maximum. Whatever's in the water at that time is the maximum. Earlier we answered a question about how much sodium chloride that would be. But everything dissolves that's near the ocean. Every solid that's near the ocean could dissolve at least a teeny, teeny, tiny little bit. Sometimes it's almost zero, basically, but a little bit. And so the sand at the bottom of your feet would be the proof that as much as can dissolve has dissolved into that ocean water. What about a supersaturated solution? If we add a crystal to the supersaturated solution, this is the most dramatic of all, right? Adding a crystal to a supersaturated will cause a dramatic crystallization, sort of a chain reaction. The crystal will cause many crystals to form, many additional crystals to form. And why? Well, a supersaturated solution holds more than it should, more than can stably be dissolved. And so when you add a crystal, all those extras, all of the excess beyond the maximum has to come out now because you've given it a place to start. That little crystal that you add has little faces, little flat surfaces and points on it, and the crystals, the ions that are in the solution, they'll start to build crystals off of that. That's why we call that a seed crystal, because it branches off many, many, many more crystals. I think you've seen that in class. If you haven't seen a supersaturated crystallization process in front of you yet, or you missed when we did it, make sure to ask. I've got some things I can show you that can help you see that up front. Two more. We've got some with titrations at the end to wrap things up. You've titrated 21.5 milliliters of acid using a base. And remember, we want to look at these stories. We want to look at our acid to base sort of ratio. This acid has 2 hydrogens. This base has just one OH group. Remember, those are the two things that we're comparing to each other. That's not going to work. 2 H's need 2 OH's for this to work. So in our equation, our acid, H2SO3, is going to need 2 lithium hydroxide, that's our base, in order for this to work. This is an important ratio then. In order for the hydrogens from one and the hydroxides from the other, these 2 hydrogens will need these 2 hydroxides, okay, to work out together, and those will make 2 water molecules. In order for that to work, we're going to need to use that 2-to-1 ratio. It also mentions that you've recorded some burette readings here. Remember, that tall, skinny burette's going to give us some numbers. And from that, we can figure out how much we use. So we're going to need to subtract these 2 values. That's our starting and our ending. And then begin our math with that difference. So if you subtract that out, 29.16 milliliters of what? Let's see, lithium hydroxide from the burette. So that's our lithium hydroxide. And what's the concentration? We've got 0.7550 moles of LiOH in every liter, or in this case, let's go with milliliters, since that's the unit that we have to start with. And then here's the key step, right? According to my equation up here, 2 moles of lithium hydroxide will be reacting for every 1 mole of the acid that's present in the solution. And that 2-to-1 ratio, of course, you're dividing by 2 here, is going to change your math. If you forgot it, you'd have the wrong answer. What does this give us? 0.01101 moles of, let's see what's left. Milliliters canceled, moles of base canceled. We've got moles of acid. And they want us to figure out the molarity of the acid. Well, we've done many, many, many of those throughout this packet. What's the volume of the acid in liters? Go back up to the top. You used 21.5 milliliters of acid. So that's your volume for down here. We need it in liters, so 0.0215 liters. And that'll give us our overall concentration of acid. When we divide it out, it's 0.512 moles per liter, or just a big M, of the acid we're talking about here. The ratio makes a great deal of difference, especially when we forget to use it, because it's always part of the math when it does exist. Okay. All right, 33. And again, let's look at the acid and the base and see if we can consider their ratios before we get too far into this problem. This acid has 1 H. This base has 2 OHs. So when we go to write our equation, the acid, HClO4, and the base, barium hydroxide, we're going to need 2 of the acid, right? 2 H's to go with 2 OH's over here. So this is a 2-to-1 ratio as well, except in this case it's 2 acids for every base. They also give us the starting volume, which we'll use later in our math. But they also give us these two readings off the burette again. So again, start out with a subtraction. Subtract those 13.15 milliliters of the acid in the burette. So that's our HClO4. It's perchloric acid. And that's a concentration of 0.6 moles for every 1,000 milliliters again. When you're doing these kind of calculations, it's pretty important that you label things, okay? Because we have HClO4, like so. Because we're going to have a mole-mole ratio. All right, so we need to then consider in our reaction there will be 2 moles of HClO4, according to my equation, for every 1 mole of base. All right, how many moles does that come out to be? Plug it and chug in my calculator, 0.003945 moles of base. And what was the total, what was the original volume of that base? 9.22 milliliters. I'm going to go up here and I'm going to move that decimal over 3 times to get to liters, right? 1, 2, 3, 0.00922. This is a place that students often make mistakes because they leave out a 0 or something like that. 0.00922 liters for a final molarity of 0.428 moles per liter. Barium hydroxide. Or, again, as usual, you can just write that as 0.428 and then a capital M in italics if you have that font in your pen. Okay. Guys, that's the end of that packet. There's a lot of problems in there. I appreciate your working through these and trying as many as you can. And if you've watched all the way through this entire video packet, you're hearing me now. Thanks for all your hard work and solutions and throughout the year. If you have more questions, stop and see me in class, and I'll talk to you then.